Hello everyone, my name is Ramesh Parsewar. I am currently studying in IIT BHU, BTech in Computer Science. Uh, so today we will see the NCERT chapter number 5, Work, Energy and Power. Uh, so in work, energy, power, work means uh, work done is given by force into displacement, and whenever we utilize energy and do something, means in the physical context, means move any object, or there is displacement of the thing on which force is applied, then work is done on that object. And energy and work are very much related, because means energy is the ability to do work. Means there can be potential energy, kinetic energy, chemical energy, heat energy. So there can be different type of energies, and it is basically the ability to do work. Means whenever you do some work done, then energy is utilized in it. And power is nothing but the rate of work done, or the rate of utilization of energy. So it's work done per unit time, or you can say energy consumption per unit time. So now we will see the NCERT exercises of this lesson, work, energy and power. So here is the first question. The first question says that the sign of the work done by a force on a body is important to understand. Yes, definitely, because work done is the dot product of work done is dot product of force and displacement. So as it is the dot product of two vectors, means it will be given by F into d cos theta. So as here theta will be the angle between force and displacement. So if this means cos theta, depending, it is between 0 to 90, it will be positive. If it is 90 degree, then the work done will be 0. And if theta is greater than 90, between 180, so it will be negative. So work done depends on the directions of force and displacement vector. So it is necessary to analyze it. So the question says we have to check whether the work done will be positive or negative. So the first uh, exercise is that work done by a man in lifting a bucket out of a well by means of a rope tied to the bucket. So in this case, the work is done by the man on the bucket. So if we take this to be a bucket, then downside mg is acting upon it, and upside the man is applying the force. So in this case, the as the man is lifting it up, it is given, so the bucket will be going up. So the direction of displacement is upwards, vertically upwards, and the force applied by the man is also upwards on the rope. So the work done by the man in lifting this bucket will be positive, as the angle between the force and the displacement is between 0 to 90. It is actually 0 in this case, so it will be positive. Now in the second case, it is given work done by the gravitational force in the above case. So in the same case as above, it is asked what is the work done by the gravitational force. As the gravitational force is here mg, it is acting downside, and the force is applied vertically upwards. So here we can see there is 180 degree angle between force vector and the mg vector. So the cos theta in this case will be negative, and the work done by the gravitational force will be negative. Now the third part says work done by the friction on a body sliding down an inclined plane. So here we take one inclined plane. The third case, we have one inclined plane, and on that one body is sliding downside due to the gravitational force. But it is said that the there is friction, that is this inclined plane is actually rough, and so there will be a friction acting backside on this body. So it is asked what is the sign. So in this case, it is clear that the displacement will be in this direction, and friction is opposing it, and it is correctly 180 degrees behind, means directly opposite. So in this case, the work done will be negative. Now, D part says work done by an applied force on a body moving on a rough horizontal plane with uniform velocity. So here it is a rough horizontal plane, and on that one body is given, and it is said that one applied force it is there, and we have to check for the work done by the applied force. As the body is moving with uniform velocity, so it is moving in the direction of the force which is applied. So the direction of movement, that is the direction of velocity and force, is in the same direction. So in this case, uh, the work done will be positive. Now, work done by the resistive force of air on a vibrating pendulum in bringing it to the rest. So, in E part, it is asked that there is a pendulum, and it is vibrating, and means it is oscillating like this, and there is resistive force of the air as it is in the original case. Means whenever we will oscillate such a pendulum, then obviously after some time it will stop due to the resistive force of air. So in this case, what happens that when the pendulum is coming towards the mean position, or it is going towards the extreme position, uh, the resistive force of the air will be in the opposite direction to the direction it is coming. So in this case also, the work done by the resistive force of air will be negative. Now we go for the next question. So the next question is, a body of mass 2 kg is initially at rest, moves under the action of an applied horizontal force of 7 Newton on a table with coefficient of friction 0.1. So some things are given to us. It is given that the body has mass 2 kg, m is given 2 kg, and it is given the force applied is 7 Newton, and coefficient of friction, that is mu k, is given to be 0.1. Now we have to compute some work done in this case. So we'll draw the free body diagram of the body. So here mg will be acting downside. So in this case, I'm taking g to be 10 meter per second square. So mostly in most cases, you have to take G10 only, means if it is not otherwise mentioned. But as per the question, means what the G value is taken. If it is explicitly mentioned that you have to take 9.8 meter per second square, then you have to take that, or the given value. I'm in this case taking G to be 10. So mg will be 20 Newton, and the force is applied is 7 Newton. So as it is said that there is kinetic friction, so there will be a opposing resistive force of friction due to this coefficient of kinetic friction 0.1. It will be given by mu k mg. So it will be 0.1 times 20, that is nothing but 2 Newton. So we can say that F net on the body will be equal to 5 Newton. So now the work done by the applied force we have to calculate. So in this, we actually firstly need the displacement of the body. So as we know, for displacement, we will need to use kinematics. So for that, firstly, we will need the acceleration of the body, which we will calculate by the F net. So acceleration will be given by force by mass, which we know by our previous knowledge. And this will be equal to 20 by, sorry, F net is 5. So 5 by 2, which is nothing but 2.5. So now, if we have acceleration, now we can use the equations of motion. So we know for displacement, we can use S is equals to ut plus half at square. But in this case, it is given that the body is initially at rest. So in this case, u will be 0. So S equals half at square, as ut term will be 0. So it will give the displacement for 10 seconds. If we put the value half into 2.5 into 100, it will come, which comes out to be 250 by 2, that is 125 meters. So displacement will be 125 meters. So the work done by the applied force we will calculate. So the applied force is 7 Newton. Here it is given 7 Newton. So work done will be F into T, or F into S, as we have taken displacement S. So it will be 7 into 125, which comes out to be 875 joules. So next we have to calculate the work done by the friction. As we see here, the friction is 2 newtons. It is what we have calculated, and it is in the opposite direction of the force applied. There is 180-degree angle between the two vectors. So work done will be Fs cos theta, which will be 2 into 125, and cos theta will be minus 1. So it will be minus of 250 joules. So in the C case, we have to calculate the work done by the net force. So it is given so what we have calculated here, the net force comes out to be 5 Newton. So we have to calculate the work done by this, and the net force direction will be in the direction of the displacement. So the angle will be 0 degrees. So cos theta will be 1. That is nothing but work done equals Fs cos theta. So F is 5 Newton, and S, that is displacement, is 125. So the work done in this case will be 625 joules. Now here it is asked what is the change in the kinetic energy of the body in 10 seconds. So we need the change in the kinetic energy. So we need kinetic energy, which is initially of the body, K initial. So as we know, the body was initially at rest, so kinetic energy initial will be 0. But now the force is applied, it accelerates and attains certain velocity after 10 seconds. So this kinetic energy is actually acquired by the work done by this applied force, and means it will be by the work energy theorem. We know that the change in the kinetic energy will be the work done by the net force, means net external force. So the applied force and the friction, due to both of these, there will be work done, and the net work done will be given by the net force, which is 625 joules. So the kinetic energy final means will be 625. So delta Ke by the work energy theorem is 625. Now we will move forward to the next question, which says that we have given some figures here. So it is said that in figure 5.11 are examples of some potential energy function in one dimension. The total energy of the particle is indicated by a cross on the ordinate axis. So it is Vx versus x, that is potential energy is denoted by V. So these are the graphs of potential energy. Yes, it is some function of x, and it is said that by this cross on the y-axis or the ordinate axis, they have shown the total energy of the particle. In each case, specify the regions, if any, in which the particle cannot be found for the given energy. So in this case, we have to firstly determine that in which regions of this graph, of this curve, there will be means the particle cannot exist. And then also indicate the minimum total energy of the particle must have in each case. Think of simple physical context for which these potential energy shapes are relevant. So firstly, we have to check for which regions the particle will not exist. So the main thing in this question, which is need to be means kept in mind, is the concept that the total energy is given by kinetic energy plus potential energy. E is equals to K plus U. And we know that kinetic energy is always positive. So this is the most important thing for this question. K equals half mv square, which will be always positive. It will be always greater than equal to 0. So this is the actually the main condition in this question, that K is greater than equal to 0 is the main condition for checking in which regions the particle can exist and which regions it cannot exist. So as K is greater than equal to 0, and by this equation E is equals to K plus U, we can say that K will equals to E minus U must be greater than equals to 0. So from this equation, we can say that E will be greater than equal to U. So E must be greater than equals to potential energy, means the total energy should be greater than equals to the potential energy so that the particle will exist in that region. So in the first figure, it is here where the total energy is. By this cross, it is shown, and the V naught is the potential energy. Means after x equals to before a x equals to a, the potential energy is 0, and after x equals to a, the potential energy is V naught, which is by the graph it is greater than E. So in this case, the particle for the first figure, the particle will not exist for x greater than equals to A. So for x greater than equals to A, the particle will not exist. Now the second figure shows here the total energy is here. It is shown by this cross. And we see that in the graph, there is actually no region where the total energy is greater than this potential energy. Means everywhere in the graph from minus infinity to infinity, we can see that energy is always lesser than this given function. So in this whole region from minus infinity to infinity, in this all region, the particle will not exist. Means there is no such reasons for existing. So here it will be from minus infinity to infinity. Now in the third figure, so here we have the third figure. In this, the total energy is here, and by this curve, we can see that in the region which is between A and B, in this region, the potential energy is minus V1, and it is definitely less than E. Obviously, it is less than E. So in this region, the particle will exist, and in all other region, we can see that it is V naught and it is greater than E. So the particle will not exist. So the answer for this will be x less than A and x greater than B. X greater than B. Now the fourth figure, in this case, the there it is shown E. So they have also given one dotted line to show up to which coordinate the energy is greater than the potential energy, and after which the potential energy is greater than the total energy. So from this curve, it is clear that the regions where total energy is less than the potential energy is the region from minus b by 2 to minus a by 2, and the region from a by 2 to b by 2. So it will be x greater than, so it will be minus b by 2. It's x greater than minus b by 2 and less than minus e by 2. And x greater than a by 2 greater than A by 2 and less than B by 2. Now, the second part of this question says that if we have to also indicate the minimum total energy of the particle must have in each case. So, what can be the minimum energy means which can be there for the particle? So, in the existing regions, in the non-existing regions where the particle does not exist, so there is no case to address that. In the cases where means the regions where the particle exists, like in the first figure, it exists for x less than equals to a. So for x less than a, it exists. So in this region, what can be the least total energy? So as we know that energy must be greater than equals to the total energy must be greater than equals to potential energy. So at least it can be how much? It can be E greater than equals to U means it can be least equals to the potential energy. So in the first case, we will see that the least potential energy in this region of x less than equals to A is 0. So the total energy which can be least taken is 0. Now in the second case, there is no existing region, means the particle does not exist in any region, so we cannot comment on this because there is no existing region. So even if we want to exist, so the least energy, like if we want to exist the particle in the region negative x means x less than 0, then this region which is a little up than the cross, this much but total energy must be given to the particle. So this will be the least energy in this case. In the third case, the particle must have at least minus v1 amount of energy, because for existence it must be greater than equals to potential energy, and the least potential energy is minus v1. So the least total energy it can have is minus v1. And in the fourth case, the least it can have is same like this case, the least potential energy minus v1. So in this case also it must have at least minus v1 amount of energy. So now we move on to the question 5.4. In this question it is asked the potential energy of function for a particle executing linear simple harmonic motion is given by Vx equals to half kx square. So the equation for the linear simple harmonic motion, which we will which there will be in the 12th standard simple harmonic motion. So it is given Vx equals to half kx square. This equation is given for this curve for the potential energy function, where k is the force constant of the oscillator, and the value of k it is given 0.5 Newton per meter. The graph of this is shown in the figure. Show the particle, show that the particle of total energy 1 joule, it is given total energy 1 joule, moving under the potential energy, moving under this potential, must turn back when it reaches x equals plus minus 2 meter. So in this case, we have to show that the particle can exist only from x greater than equals to minus 2 to less than equals to 2. So again, this is much similar to the question which we saw before, 5.3. In this case, we also use the same thing, that T equals K plus U, and here the total energy it is given 1, and K is, we'll assume K to be K, and the potential energy is given by this function half kx square, half kx square. So, and from this we can see that k will be equals to 1 minus half kx square. This k is of kinetic energy, it's capital K, and this k is the small k, which is given the force constant of the oscillator, half k x square. So from this if we'll calculate this half kx square, now we know that k will be greater than equals to 0, means the kinetic energy can either be 0 or it can be positive. It can never be negative. So we have one constraint for this equation. 1 minus kx square should be greater than equals to 0. So if we will evaluate this equation, then we will see after putting the values of k that x square must be greater than equals to 4. X square should be less than equals to 4. So from here we can say that x must be from -2 to 2. So the basic concept in this is that the total energy is equals to total kinetic energy plus potential energy, and kinetic energy is always positive or 0. So putting this constraint, we will get that x is from -2 to 2. Now we move on to our next question, which is 5.5. Now in this case, it is asked that the casing of a rocket in flight burns up due to friction, at whose expense is the heat energy required for burning obtained the rocket or the atmosphere. So now it is told in this question that a rocket is in its flight and it burns up due to friction, means in the atmosphere it is flying and due to friction it burns up. So as it is burning, there is heat energy which is released, means, and it is asked at whose expense this heat energy is coming for the burning. It is asked whether it is rocket or whether it is atmosphere. So in this case, we should know that who is doing the positive work. So in this case, uh, if we will consider rocket which is moving and it is having some resistance due to air drag. So as this rocket is moving, it is having uh, resistance due to air drag with the atmosphere, and it is burning due to the friction which is occurring on its surface. So in this case, we see that the force applied by the rocket, means the force applied on the rocket is in this direction, and the displacement of the rocket is also in the same direction. So the force on the rocket and its displacement is in the same direction. So the work done by the rocket is actually positive. And so as the work is done by the rocket, so the energy of rocket is utilized. And so it is by the expense of rocket. And we can also understand this by other way that the energy of the rocket is consumed, means the total energy of the rocket will go on decreasing as it is burnt up. As the fuel is burnt up, the and the rocket's total energy will go on decreasing. So this total energy which is utilized is actually used in this work done, and so the burning happens of the surface is on the expense of the energy which is given by the rocket and not by the atmosphere. Now, the second question is comets move around the sun in highly elliptical orbits. The gravitational force on the comet due to sun is not normal to the comet's velocity in general. Yet the work done by the gravitational force over every complete orbit of the comet is zero. Why? So it is said that the comet is moving around the sun in a highly elliptical orbit, and the force which is acting on the comet is gravitational force. And so as the force is acting and the comet is moving, there is displacement of comet, there is acting a force. So there will be some work done by that force. But it is said that the in one complete orbit, means one complete revolution, the work done comes out to be zero. And it is also said that always the the force, the gravitational force is not normal to the comet's velocity. So now in this case, actually, one might think that that work done might be zero the because it is given by Fs cos theta, F dot D, F dot S, or Fs cos theta, the dot product of the vectors, force vector and the displacement vector. So for it to be zero, if the F is not zero, if uh, displacement is not zero, force is not zero, so cos theta must be zero and theta must be 90 degree. So if it would have been perpendicular, then it would have been zero. But it is said that even at means even it is not normal to the comet, means the displacement of the comet, then also the work done for the complete orbit comes out to be zero. Actually, in this case, this gravitational force is an internal conservative force of this system, this sun and the comet system. So there is what we know the concept of potential energy for internal conservative forces, and it says that the potential energy, the change in potential energy is nothing but the the negative of the work done by the internal conservative force. So the work done by the internal conservative is equals to minus of delta U. That is nothing but the negative of the change in potential energy. Or we can say the change in potential energy is negative to work done by the internal conservative force. But now in this case, we see that there is one complete orbit. And in that orbit, the potential energy as the gravitational potential energy will not change when it will come to the same point after orbiting. So it will be at the same distance from the sun. And so the potential energy, there will be no change. So there will be no work done by the conservative force. It will be zero. And another thing which we must know that as the gravitational force is a conservative force, and we know that the integral of a conservative force over a closed orbit means a closed path is always zero. That is what the definition says for the conservative force. So definitely if there is a complete orbit, so the work done, the net work done by this conservative force will be zero. Now the third part says an artificial satellite orbiting the earth in very thin atmosphere loses its energy gradually due to dissipation against atmospheric resistance, however small. Why then does its speed increase progressively as it comes closer and closer to the Earth? So it is said that the artificial satellite is orbiting the Earth. The artificial satellite is orbiting the Earth. So here it is Earth, and the satellite is orbiting the Earth. So, and it is said that there is dissipation of its energy due to the atmospheric resistance. It is given that it is small in amount, and so the total energy is decreasing gradually, and the orbit is becoming smaller as the satellite is coming closer and closer to the Earth due to dissipation of energy. But then also its speed is increasing. So this is a point where we can have some type of question that why the speed is increasing even if the energy is decreasing, the total energy is decreasing. So in this case, we know that total energy is given by kinetic energy plus potential energy. And in this case, actually, it is happening that as the orbit means, firstly, we need to understand that the potential energy is now the function of the distance. And as the distance becomes less and less, the potential energy goes on becoming less, more and more negative. The potential energy goes on decreasing as it comes closer and closer to the Earth. It becomes more and more negative. So this term is becoming more and more negative, it is decreasing. And it is given that the total energy is decreasing, but it is very small amount. Here it is given that it is, however, small. So it is decreasing less compared to this potential energy. So due to this, we will see that if total energy decreases by less amount and potential energy decreases by more amount, so in that case the kinetic energy will actually increase, and so the will increase. Now we have in the D part that a man walks 2 meter carrying a mass of 15 kg on his hands in figure. So it is shown in his hand. It is he's holding a 15 kg mass and he's moving in some displacement. He's doing of 2 meter, and in another case there is a wall, means some sort of like in the well, how we lift the bucket. In the same type, the man is pulling this rope and the weight is being lifted. So for these two cases, we have to tell in which case the work done will be greater. So in the first case, actually, there are two forces which are acting on this mass. Means there is mg acting downside, and the man is holding this, and the displacement is occurring in this direction. So the displacement is horizontal for the first case. The displacement is horizontal 2 meter, but the force which is acting on this body, that mg force, the weight of the body is acting downside. So the work done on the body due to this gravitational force will be zero, as the angle between this force vector and the displacement vector is 90 degree, and cos 90 is zero. So the work done in this case will be zero. But in the second case, actually, the block is being lifted by the man. So as he's lifting, he's applying the force here horizontally, but over the pulley, the rope is applying a force on it upside, and the displacement is also occurring upside. So the force and the displacement are in the same direction. So the force which was acting will be definitely 150 Newton. Yes. If we take G to be 10, so mg will be equals 15 into 10, that is nothing but 150 Newton downside. And for lifting it up, the equal and opposite force 150 Newton must be applied by that man so that it is going up. So if you consider 150 Newton, means if there is no acceleration, we considered downside also 150 Newton and upside 150 Newton. So for 2 meter of displacement, of the vertical displacement, there will be a work done of 300 joules. Work done, which is be given by this force 150 Newton, this force 150 Newton into displacement, which is 2. So there will be a 300 joules work done. So definitely in the second case, there is more work done. Now we move on to the next question, which is 5.6. In this question, it is asked to underline the correct alternative. So the first question says, when a conservative force does positive work on body, the potential energy of the body increases, decreases, remain unaltered. So now this is a thing which I told in the previous question, that the work done by the conservative forces is the negative of the change in the potential energy. So this is means this concept is used in this question. It is asked that the conservative force does positive work on the body. So this is positive, but the change in potential energy will be negative of this. So the change in potential energy will be definitely negative. As the work done is positive, change in potential energy will be negative by this equation. And if the change in potential energy is negative, it means that the potential energy is decreasing. Means we need to underline here to decreases. The potential energy decreases. Now, work done by a body against friction always results in a loss of its kinetic potential energy. So, potential energy we know is due to the conservative force of any system, there is internal conservative force, and due to that, there is potential energy. So, potential energy of any system will only change when there is some kind of work done. By this equation, we can relate to it that only when there is work done by the internal conservative force, then only there will be potential energy change. And friction actually opposes the relative motion. Means as the body is moving, the friction will oppose or resist the motion. It will decrease its speed. So as the speed decreases, therefore the kinetic energy will decrease, and there will result in loss of kinetic energy. The rate of change of total momentum of many particle system is proportional to the external force, sum of the internal force on the system. So now this is a thing from the previous chapter of the force that regarding force and momentum. The rate of change of total momentum of many particle system is proportional to the external force or the sum of the internal forces on the system. So we know that the rate of change of total momentum of the many particle system, it is independent of the sum of the internal forces. The internal forces have no role in the change of the net momentum, the total momentum of the many particle system. It is the external force which changes the total momentum. The internal forces will cancel on each other and will have no effect on the momentum, total momentum. Now, in an inelastic collision of two bodies, the quantities which do not change after the collision are the total kinetic energy, total linear momentum, total energy of the system of the two bodies. So for inelastic collision, what we know is that there will be deformation of the bodies which are colliding. And in that deformation, some of the energy will be lost. So the total kinetic energy or the total energy will not be conserved. But for any kind of collision, may it be inelastic or elastic, one thing which we must remember is that the total linear momentum of the two bodies will remain constant. So this was this question 5.6. So now this next question is 5.7, which states that now state if each of the following statements is true or false. Give reasons for your answer. So we have to state if it is true or false and reasons for that. So the first statement is in an elastic collision of two bodies, the momentum and energy of each body is conserved. So this statement is definitely true. For the elastic collision of two bodies, the momentum of and energy is conserved, but here actually it is asked the momentum and energy for each body. If for the system it would have asked, so definitely then our answer would have been true. So this kind of confusion might occur sometimes, but we have to clearly check what the question asks. So we know that for the system in any collision for the system, the momentum remains conserved, and for elastic collisions particularly, momentum and total energy of the system will remain conserved. But for now this question, it is asking for each body. So definitely for each body, the momentum and energy will not be conserved. This will not be the same. There will be change in the momentum and change in the energy. As we see, if we consider two bodies here, two bodies we consider which are moving, and when there will be some collision, so there will be change in these velocities v1, v2. If you consider these velocities, there will be definitely change in these velocities when the collision will occur, even though the system's total momentum is conserved, and for elastic collisions the total energy is also conserved, but these velocities will not be same. So the energy and momentum for each body means for these bodies separately, the momentum and energy will not be conserved. Now, the second statement says total energy of the system is always conserved no matter what internal and external forces on the body are present. So, this question is definitely so. Total energy of a system is always conserved no matter what internal internal external. But this statement is wrong, as we know that the work done by the external forces is means gives the change in the total energy. Means the total energy changes due to the work done by the external forces. So this statement is false because of that reason. So it is not conserved for the system if there is some external force acting on the system. Now the third statement says work done in the motion of a body over a closed loop is zero for every force in nature. Now this is also false because this statement is for the conservative force. Work done in the motion of body over a closed loop is zero for the conservative force. For non-conservative force, the over the closed loop also the work done will not be zero. So this statement is false. Now the fourth statement is in an inelastic collision, the final kinetic energy is always less than the initial kinetic energy of the system. So this question is means somewhat tricky, we can say. So definitely the in elastic collision, the total energy of the system will be lost. Means there will be some loss in the total energy of the system, which is due to the deformation of the bodies. But definitely, as the total energy is the sum of kinetic energy plus potential energy, we cannot say that the final kinetic energy will always decrease. So it may happen that the total energy decreases, but the kinetic energy increases and potential energy decreases much. So due to this, we, we say that means the statement will be false. Means it is not always that the kinetic energy will be less. The total energy will be less, but the kinetic energy may have increased if the potential energy decreases much. Now the 5.8 question. In an elastic collision of two billiard balls, is the total kinetic energy conserved during the short time of collision of the balls when they are in contact? Now, for the 5.8 question, it is regarding collision of this balls. It is the elastic collision it is given. We know that for every instant the momentum is conserved, but the total kinetic energy will definitely will be same initially and finally of the whole system. The total kinetic energy initial will be equals to total kinetic energy final. But during the collision, the instant which is asked when they are in contact, these elastic means these billiard balls will be in contact. There will be some kind of here they will when they are in touch, they will squeeze each other. So there will be the elastic potential energy which we will get from this total energy, and the some part of kinetic energy will change to this elastic potential energy, and therefore the total kinetic energy at this instant will not be same. Now the second question says, is the total linear momentum conserved during the short time of an elastic collision of the two balls? Yes, the total linear momentum, however short the interval, will be the total linear momentum of for the elastic collision of the two balls or any collision will be conserved. Now the third question is, what are the answers to A and B for inelastic collision? So in the case of inelastic collision, the linear momentum, as I said, for any collision, it will be conserved for any time interval. But as in case of inelastic collision, as the total kinetic energy itself is not, means the final kinetic energy and the initial total kinetic energy are not equal. There is some loss in the kinetic energy or the total energy. So in this case, the first case will be no only for this part also. Now the D part says, if the potential energy of the two billiard balls depends only on the distance between their centers, is the collision elastic or inelastic? Note, we are taking here the potential energy. So it is given the same thing that during the contact when the collision is there, there will be the elastic potential energy. So if it is considered as depending on the separation distance, it is asking whether the collision will be elastic or inelastic. As there will be potential energy and there is no permanent deformation, it is due to the elasticity of the ball. So the collision will be elastic in this case. As the total energy will for some time change to the means some of the kinetic energy will change to potential energy, but after the balls separate out, means after the collision, the potential energy will be regained in the form of kinetic energy and the total energy will remain conserved and the collision will be elastic. Now, the question 5.9. A body is initially at rest. It undergoes one-dimensional motion with constant acceleration. The power delivered to it at time t is proportional to. So it is given that body is under one-dimensional motion with constant acceleration. So for constant acceleration, we can use the equations of motion. And from that, as we are concerned with the power, so power is work done per unit time. Power is work done per unit time. It is nothing but F dot ds integral of F dot ds by t. So for infinitesimal time, we can say that F dot ds upon dt if the time is infinitesimal. Means, the displacement is infinitesimal and the time is very short time period we take. So the instantaneous power will be F dot ts by dt, which is nothing but F dot v, which is nothing but F dot v. Is the force vector dot product with the velocity vector will be the instantaneous power. So now in this question, it is asked the proportionality of t, the power delivered to it at time t is proportional to. So the power proportionality with time. So for this, as the acceleration is constant, F can be given as F is equals to ma. And as it is constant, there is no time dependency. Mass into acceleration. Acceleration is constant, there is no time dependency. But the velocity will be given as v is equals to at. So there is a time dependency here in velocity at. So if we put this here f dot v ma dot at, from here power comes out to be proportional to t to the power 1. That it is proportional to t. It is directly proportional to t. Now 5.2 is somewhat similar to 5.9. Here also it is asking a body is moving unidirectionally under the influence of constant power. Now in this case the power is constant and we are asked to tell the displacement in time t is proportional to, means the time proportionality for distance. So power is constant and now we consider the body is moving unidirectionally. We are considering it's a free body and it is moving. It has only kinetic energy. No potential energy means the total energy we are considering equals to the kinetic energy as body is given a free body. And so the total energy equals kinetic energy equals half mv square. And it is given that the power delivered is constant. And we know that work done, which is nothing but the change in kinetic energy, delta k equals power into time. As power is work done per unit time, as it is work done per unit time, work done equals power into time. As the power is constant, so kinetic energy is proportional to t. So we can say kinetic energy is proportional to t. So half mv square is proportional to t. From here, we say that v is proportional to root of t. And now the displacement it is asking, and we know that displacement t is equals to v into t. So considering that v is proportional to root t, we can say that t is proportional to root t multiplied by t, which is nothing but nothing but t to the power 3 by 2, which is the third option. So option number 3 will be correct. Now 5.11 question. A body is constrained to move along the z-axis of a coordinate system is subject to a constant force F given by F equals to minus I plus 2J plus 3K Newton, where I, J, K are unit vectors, where the X, Y, Z axis of the system respectively. Now it's a simple question where the force vector is given. We have to just use the definition of work done, which is nothing but F dot ds, integral of F dot ds, integral F dot ds. We are given the force vector to be minus I plus 2j plus 3k. And as the force is constant, it is given, this is constant force it is given. So we can take out from the integral and it will be F dot in F vector dot integral ds, means integral of the displacement, which will come out to be F dot s, F dot s. Now, as it is given, the work done with the force in moving the body a distance of 4 meter along the z-axis. As it is moved 4 meter along the z-axis, the displacement will be 4k cap. So we can write displacement as, now work done will be F dot S, which you can take the dot product minus I plus 2j plus 3k in dot 4k. As we know, I dot k is 0, j dot k is 0. Only the k component or the z component will have the work done 3k, as k dot k is 1, 3k into 4k dot 4k. K dot k is 1, the other are 0, I dot k, j dot k 0. So the work done will be 12 Newton, 12 joules. Now the next question is, an electron and a proton are detected in a cosmic ray experiment. The first with kinetic energy 10 keV and the second with 100 keV. Which is faster, the electron or proton? Obtain the ratio of their speeds. So firstly, we are given the kinetic energies for electron and proton. For electron, it is given 10 kiloelectron volt, and for proton, the kinetic energy is 100 kiloelectron volt. Now, it is asked whether electron is faster or proton is faster, and also the speeds ratio is also asked. And the necessary things like the electron's mass, proton's mass, and the conversion from electron volts to joules is given. So, firstly, we will write for the equation for kinetic energy, that is nothing but K equals half mv square, half mv square. So V equals under root 2k by n. So V equals under root 2k by n. So from this equation, for both the cases, we have to calculate the velocities. We have to just put the in the equation the value of kinetic energy, the value of mass, which is given. Like for the case of electron, V equals under root of 2 times k, it is 2 times k, which is nothing but 10 kiloelectron volt. So 10,000 electron volt, and the conversion for electron volts, it is given 1.6 into 10 power minus 19 joules. So in the standard units, SI units, you have to take the kinetic energy 1.6 into 10 to the power minus 19 joules, and the mass of electron, which is nothing but 9.11 into 10 power minus 31. 10 power minus 31. So if we will calculate this, we'll get the velocity of electron. And in the same way, we have to calculate the velocity of proton. So after calculations, you can check the velocity of electrons PE will come out to be 5.93, 5.93, 5.993 to 10 to the power 7 meters per second. So this will come out to be the velocity of electron, and the same way velocity of proton will come out to be 4.38 into 10 power 6. 4.4.38 into 10 to the power 6. So even though the kinetic energy proton was looking to be greater, but we know that kinetic energy is more dependent on mass and velocity. So even the velocity of proton is less due to its mass, heavier mass, which is much higher, nearly 1800 times or more than 1800 times. It is heavier than electrons. So therefore the kinetic energy was greater. But after from the calculations, we see that the velocity of electron is much higher, and you can calculate the ratio of V is to VP, which nearly comes out to be 13.54 is to 1. So you have to just take the ratio of this, which nearly comes out to be 13.5 is to 1. Now, in the question 5.13, a raindrop of radius 2 mm falls from a height of 500 meter above the ground. It falls with decreasing acceleration due to the viscous resistance of air until at half its original height it attains its maximum terminal speed and moves with uniform speed thereafter. What is the work done by the gravitational force on the drop in the first and second half of its journey? What is the work done by the resistive force in the entire journey if its speed on reaching the ground is 10 meter per second? So in the normal case, where we consider no atmospheric effect, but in this case, it is said that the raindrop is falling, but there is atmospheric effect. There is a deceleration of the raindrop. So there is a deceleration of the raindrop due to the atmosphere. And it is said that after traveling half of its height, which is 500 meter, it achieves its terminal velocity, which will be constant after that, and moves with the uniform speed. So we are asked three things. First is the gravitational force work done in the first half of the journey, second half of the journey, and the work done by the resistive force. So here, firstly, we need to have the mass of this raindrop. For that, we know that the raindrop is spherical in shape and its radius is given to be 2 mm. So we have to use the formula for mass to be V into rho, where V is volume and rho is the density. As rho, the density of water is not given, but commonly we take it to be 1000 kg per cubic meter. So that is what we will be taking here. And the volume can be calculated for a sphere for the raindrop by the formula for calculating volume, which is V equals to 4 by 3 pi r cube. 4 by 3 pi r cube. So we have V here, and rho, we will take rho equals 1000 in the SI units kg per cubic meter for water, as a raindrop is made up of water. So from this, we will get the mass of that raindrop. And when you will do the calculations, the mass comes out to be, so the mass will be 3.35 into 10 to the power minus 5 after calculations. And this is the mass which you have to take. And now for the work done by the gravity, thing which we need to know is the work force of the gravity, which is mg, which will be this mass m equals to 3.35 and 10 power minus 5 kg into g, which we will be taking 10, g equals to 10, or we can take more accurately g to be 9.8. So it depends. Mostly we have to take 10, but for more accuracy, we are taking 9.8, and we'll get mg, and the force will be mg, and the displacement, it is firstly asking for the first half of the journey, means the half of 500, which is nothing but 250 meter, will be the displacement in the first half. The same will be the second half. So as there is no change in mg or the displacement in both the journeys, first half journey and second half journey, so the work done will be same for both the cases. It will be mg into 250, which is nothing but, after calculations, it will come out to be 0.082 joules. So in both the cases, as the displacement is same, the mg work force is same, the work done will be same, 0.082 joules. Now it is asked, what is the work done by the resistive force if its speed on reaching the ground is 10 meters per second? Now the terminal velocity was achieved, and it moved with the uniform speed, and on ground it was reached with the speed. It reached with the speed 10 meter per second. So the kinetic energy can be calculated. As the initially means the drop is falling, it was initially it had zero kinetic energy, and finally it is having kinetic energy due to this velocity, means so the delta k will be final kinetic energy minus initial is zero, and final will be half mv square, and v is 10 meter per second on the ground. So you can calculate half mv square, which is which will be the change in kinetic energy, and this comes out to be 0. This is 1.675 into 10 to the power minus 3 joules. 1.675, 1.675 into 10 to the power minus 3. So this is quite small actually, means nearly large amount of energy is actually utilized against the resistive force, which we will now we will use the work energy theorem, that the work done by the net external force is equals to the change in kinetic energy. As we know, the work done by the gravity is 0.082 into 2, means for the both the cases, if we'll add for the first half of the journey and second half, we'll get it work done by the gravity plus work done by the resistive force equals delta K. Change in kinetic energy equals to work is the net work done by all the forces which are acting. So work done of the by the gravity is given by 0.164, 0.164. And the work done by the resistive force, which we calculate WR, equals 1.675 into 10 power minus 3. 1.675 into 10 power minus 3. So calculating this, you will get VR. It's nearly, it will be same. If we'll consider this to be nearly 0.2, 0.16 rounded to the first decimal place 0.2, then the work done by the resistive force will be 0.162 joules. It's nearly all of the energies is the work done by the gravity is utilized against the doing work against the resistive force, and it is attaining a little kinetic. Now 5.14 question. A molecule in a gas container hits a horizontal wall with speed 200 meter per second and angle 30 degree with the normal, and rebounds with the same speed in momentum conserved in the collision. Is the collision elastic or inelastic? So now in we know for any collision, the momentum will always remain constant, means the momentum will be conserved for the system. So in this case, the system is actually that wall and that molecule, means the gas container's wall and gas molecule form the system here. And it is given that the molecule has speed 200 meter per second and angle 30 degree to normal. So we can draw, if this is the wall, this is the normal, and it is coming 30 degree to the normal, 30 degrees to the normal. It will hit here and then rebound like this. As elastically it is rebounding to 30 degree to normal it was, and after going so. So in this case, the total momentum of the system will be conserved definitely, as in any case of collision. And the system had wall and molecule, but as the wall is very much larger, means it has very high actually weight than just a particle. So we see no means we can say yes, no recoil of the wall due to that hitting of that molecule. However, the momentum will remain conserved, and the kinetic energy of the system is also conserved. The wall doesn't gain any kinetic energy, as it is much higher, means much heavier in mass, and the kinetic energy of the molecule will be same. So definitely the momentum will be conserved. Now 5.15 question. Now this question says a pump on the ground floor of a building can pump up water to fill a tank of volume 30 cubic meter in 15 minutes. If the tank is 40 meter above the ground and the efficiency of the pump is 30%, how much electric power is consumed by the pump? So we need to calculate the electric power which is consumed by the pump. So, and it is given that the pump is not efficient, means 100% efficiency is not there. Only 30% of the energy which is provided to the pump, it utilizes against the work done. Means it utilizes in the work done, means it utilizes it to fill the tank by lifting up the water, by pumping up the water. So firstly, for this, we should know the mass of the water. And in this case, the work done by the pump is against the gravity. So the work done by the pump and the work done by the gravity will be actually equal and opposite. So work is done against the gravity. So means downside for the water, mg will be acting, and upside the pump will apply force and lift it up. So the work done here will be, or we can say that work done will be equals the change in the potential energy, as there is no change in the kinetic energy, just the water is lifted up. The work done is equals to the change in potential energy. And so all the work done which is done by the pump will be stored as the gravitational potential energy, which is given by mgh. So for this we need m, which will be given by the volume 30 cubic meter. The volume is given, and we know the density of water 1000 kg per cubic meter. So by volume and the density, we will calculate the mass. Then G will be 9.8 meter per second square, and H it is given 40 meter. So from this, we will get the work done. The work done will be mgh, which we can calculate. And then for calculating the power, the time is given to be 15 minutes. So power equals work done per unit time. So time is 15 minutes, which will take to be 15 into 60 seconds. So always remember to take all the physical quantities in their standard SI units, so that there will be no problem in the calculations. And here mgh we will take by rho vgh. Rho where will means here rho, I'm considering the density rho vgh. V is 30 and h is 40 meter, g is 9.8. So doing all the calculations, you will get the power which is required for the pump, and the power will be, since this is the ideal power which actually is needed for the work, and this comes out to be 13.067 into 10 per 3 watt. But as we know, the pump is not that efficient. Only the 30% of the power which is supplied to the pump, it is utilizing in the work done. So we can say that power output by power input, power output by power input equals 30 by 100, the efficiency. And in this case, the power output is this, as this much amount of power should be given so that work is done. And the power input is actually what we are needing. How much electric power is consumed by the pump? Consumed by the pump means the power input. So putting this value in this, you can get the power input, which comes out to be 43.6 kilowatt. 43.6 kilowatt. So this much amount of power should be supplied to the this pump, and 30% of which you will utilized. This will be that is 13.067 10 power 3 watt, and so the work will be done. Now 5.16 question: two identical ball bearings in contact with each other and resting on frictionless table are hit head-on by another ball bearing of the same mass, moving initially with speed v. If the collision is elastic, which of the following is a possible result after collision? So we have two identical ball bearings in contact. Here it is shown in the figure 2 and 3, and one is coming with velocity v. This is also shown in the figure. And the floor on which they are, it is given frictionless, and the collision by this one ball, 2 and 3 will be head on, and all three are given of the same mass. It is asked if the collision is elastic, which of the following is a possible result of the collision. So the thing which we need to consider for this question is that the total momentum of the system must be conserved after the collision. That is one thing. And as the collision is elastic, there is no loss in the energy, and there is only to kinetic energy. So the total kinetic energy before and after must be equal. These two things, which are for the elastic collision, the momentum conservation and the energy conservation, the total kinetic energy before and after will be equal. These two conditions must be satisfied for any case to happen. So we are going to check these conditions, and wherever these two conditions are satisfied, that case is possible, means can be a result. So now in first case, you see, we see is momentum conserved, means P initial was mv, means I'm considering the mass of the ball to be m. So P initial, the momentum initial was mv, and P final, the final momentum, it is mv by 2 plus mv by 2. The two masses are there, 2m into v by 2. So 2m into v by 2, which is nothing but mv. So we see the initial momentum and the final momentum are same, means the first condition is satisfied. But is the second condition satisfied? Means kinetic energy initial is, we see, it is half mv square, half mv square, half mv square, and the kinetic energy which is final. The kinetic energy final will be half mv by 2 whole square plus half mv by 2 whole square, twice of half mv by 2 whole square, which is about 1/4 of half mv square, twice of half mv by 2 whole square, which is 1/4 of half mv square, 1/4 of mv square, and the kinetic energy is half of mv square. So kinetic energy initial is not equals to kinetic energy final. So the second condition is violated. So the case number one is not possible. Now in the similar case, momentum will be conserved, but the kinetic energy is not conserved, but the collision is elastic, so this is also not possible. But if we'll consider the third case, in that case, we'll find that both the conditions are satisfied, and therefore this can be the possible result, and so the case number 2 is possible. Now here is another question for a pendulum. It is given that a bob A of pendulum released from 30° to the vertical hits another bob P of same mass at rest, how high does the bob A rise after the collision? Neglect the size of the bob and assume collision to be elastic. Now, this is a very simple question of regarding collision. So the bob will travel here and hit this ball, hit the another bob, and it is given that both have the mass m, a and b. So if we'll consider the time of collision, let anything means we don't know what will be the velocity this bob will attain now, as we have not calculated, but let it be e. This is bob A, this is bob B. So this is the thread which has become vertical now. Means it was here at 30°, but now it has become horizontal and it hits the ball B. But after momentum conservation, means if we'll say that this bob will will have some V and means V1 and this bob will have V2. After momentum conservation, initial momentum mv equals mv2 plus mv1, and energy conservation says half mv square, half mv2 square plus half mv1 square. So from this, we will see that V2 will come out to be V and V1 must be 0, as there is another thing which is coefficient of restitution, which is also for elastic collision to 1, as it is coefficient of restitution is 1, and it is given by velocity of separation by velocity of approach. Actually, for collisions, there is one thing called E, which is elasticity, means coefficient of restitution. And for elastic collisions, this is 1, and it is given by velocity of separation by velocity of approach, where the velocity of separation and velocity of approach are the things which are from the kinematics. Means velocity of separation for this case means for the case of a collision will be means uh, will be the relative velocity with which the bodies are separating after the collision, and velocity approach is the velocity with which the bodies are approaching before the collision. So for this to be one, and for these two equations to hold, the only possibility of the solving is that V2 equals V and V1 equals 0. Because if V1 equals V and V2 is V2 minus V1 by V1 equals V2 minus V1 by V. So only V1 equals to 0 and V2 equals V will satisfy this equation. And so the entire momentum of this ball will be transferred to this, and this ball will go on with velocity V, and this will come to the rest. So there is no point that it will rise after the collision. So it will not rise. It will be on the floor itself at here at rest. Now we have 5.18 question. The bob of pendulum is released from horizontal. If the length of the pendulum is 1.5 meter, what is the speed with which the bob arrives at lowermost point, given that it dissipated 5% of its initial energy against air resistance? So now in this question, it is asked what is the speed of the bob when it arrives at the lowermost point in 5.18. For this, we will use work energy theorem that the only force which will do the work means for the pendulum, there are two forces acting. One is mg downside for any pendulum which is moving. One force is mg downside, vertically down, and this tension force. But as the tension force is perpendicular always to the direction of displacement, the work done by the tension force will be 0, and there will be only work done by mg, and the work done by mg can be given by mgh, means the change in potential energy will be the work done by the gravity, which will be given by mgh. So the work done is basically mgh, and mgh can be calculated putting values of 1.5 meter as h and 2 mgh. But it is also given that there is some resistive force, that means air resistance is there, and dissipated 5% of its initial energy. So this potential energy, what which it had, and when it comes to the lowermost point, we know that h is zero, so the potential energy will be zero. So the net work done by the gravity will be mgh, and work done by the resistive force can be given by this, that 5% of its initial energy is utilized, means 5% of mgh is actually the, means negative of 5%, means negative of mgh 5%, minus of 5% mgh, minus 5 by 100 into mgh will be the work done by the resistive force. So the net potential energy which is changed to the kinetic energy is actually 0.95 mgh, is actually 0.95 mgh, and by work energy theorem this will be equals to half mv square. So now you can calculate by putting the values. We don't need the value of m, and it is also not given. So sometimes the things which are not needed are not given, so there is no point to worry. Sometimes it may happen that you may worry that mass is not given, but the things which are required are always given in the question, and it may happen that some point of time the mass will be cancelled out, and means these physical quantities are not needed after solving the equations. So it is better sometimes, means actually many times, to just skip the equation in the form of variables, and at last when you have the result, means like in this case we wanted the speed of v. So when we wanted v, then only you start putting the values, and only the required things will be required, means the question has given the required things 5% and 0.5, and g is the constant, so it will be 9.8. So putting the values, you will get v to be 5.28 meter per second. 5.28 meter per second. So that's it.